Hello everyone, welcome to ExamRat. My name is Shatabdi. I'm a medical student. Today we're going to discuss about power, about the law of conservation of energy. Um, so let's get started. And before we start, I just want to do a short recap of our previous class. So now, if you have by chance missed it, you can just easily go to our website and or our YouTube channel, and you have free access to the videos. So also don't forget to subscribe. Thanks. Yeah. So coming back to the topic of work, energy, and power, in the last class we have basically studied about work. How is it a product of the magnitude of the force and force applied on a body multiplied by the distance that the multiplied by the displacement that the force causes on to move that body basically. And if the force and the displacement are at an angle theta to each other, then in order to get the scalar quantity, because we know that work is a scalar quantity, in order to get that, we have to bring both the force and the displacement in the same linear position. For that, we take the cos component of force. That's why the modified formula is basically F as cos theta. We talked about kinetic energy, how every mass that possesses motion has kinetic energy, and we formulated a kinetic energy which came to half mv square. M stands for the mass of the object and v stands for velocity of the object. Okay. Lastly, we talked about how kinetic energy is related to momentum, because both are kind of momentum is actually a measure of the impact that an object has on any other thing, and that impact is due to both its mass and its velocity. At the same time, kinetic energy also is somehow related to both the mass of an object and the velocity of an object. Like a, a body in motion obviously will have velocity, whether it is constant or whether it keeps changing, accelerating, that's a different issue. But any body that is moving possesses kinetic energy. So that's why, since both of them were related to mass and velocity, we again formulated an equation which related both of them. We also talked about the fact that work done in changing the velocity of an object can also be written as the work done to change the kinetic energy possessed by an object. So we also talked about this equation. Okay, then we came to energy. We talked about different forms of energy. We talked about why we use the term energy in cases, instead of just saying the rate of doing work or the capacity to do work. Not the rate of doing work, sorry, because the rate of doing work is, you'll later get to know, it's called power. So yeah, the capacity to do work is energy. So why do we in some cases use the word work, and in some cases we use the term energy? So we came across energy. We also knew that mechanical energy is of two types. One is kinetic energy and one is potential energy. In the last class, we discussed about kinetic energy. Today, our main focus will be potential energy. Okay. So what is potential energy? The energy that is stored in an object due to its position relative to some zero position. So what is this zero position? So zero position is anything that you assign to be the zero position or the frame of reference. Okay. So like if a car is moving, so one of its frame of reference can be a tree it passes on its path. So this. So with respect to the tree, the car is moving, right? Because the tree is still. So this is a frame of reference. At the same time, another car on the road can also be the frame of reference. So in that case, what will happen is that one car will be in a relative motion with the other. Okay, so with car number 1 and 2, so now car number 1 is moving with respect to car number 2, but in a slower motion, in a slower velocity. That's why car 2 is ahead and car 1 is behind. So here we saw that there can be two frames of references. So frame of reference or the zero position here is whatever you assign to be the zero position. So if I say that the ground level is the zero position and any level above that you have to find the potential energy, then you will basically do the calculation of the potential energy from the zero position, that is the ground level, to the position of the object. Okay, so here is a small example. It is that when suppose this is the unstretched position of the spring, let's call it A, and this is when you have stretched it a bit by placing a ball with a string on the hook. So now you're very well understanding that here the arrow has moved down. So this basically means that some work has been done by the spring, as a result of which there is a displacement. And if work has been done, so you've also understood that some kind of an energy has been converted into some kind of another energy, right? So because in the previous slide we talked about how work is done when the velocity of a moving object is changed. So one kinetic energy only changes into kinetic energy, but the velocity, the magnitude of the kinetic energy has changed. Similarly, it can also be so that basically now what happens is the position of the hook has changed, right? So you have been able to pull this hook only because there was some sort of an energy that converted into kinetic energy which made the spring move, right? So what was that stored energy which got converted to kinetic energy which made this spring move? So this stored energy is basically potential energy. So the potential energy is nothing but basically the stored energy which can later get converted to any other form of energy when there is some sort of a displacement from the 0th position. Now what is the 0th position? That is up to you. It is relative. Just write it with another color so that you can remember it. This is basically relative. Okay. So now that we have talked about potential energy, we can also discuss potential energy at a height. Now when we are saying height, we obviously mean a certain height above sea level. Now why I wrote this is because here basically sea level is the 0th position, or we can write it as H0. So since here we are considering sea level as the 0th position, that's why we can calculate potential energy at any height above sea level. Okay. So what is written here, you guys can copy it down right now as in when I'm teaching, or you can just like after the video you can pause it or just like take it down. We also will be uploading the PDFs alongside the description of the video. Yeah. So here what is written is that an object increases its energy when it is raised through a height. Now why do you think that is? It is basically because, as we discussed in the previous one, that when you are moving anything, so the potential energy that was stored, that gets converted into kinetic energy, because if a body does not have kinetic energy, how will it move, right? So similarly, when you are raising something through a height, you are basically doing work on the object, right? Now, how is the work being done? It is being done because it is against gravity. Acceleration due to gravity is downwards. The earth does work on every object in this world by pulling it down, right? So it is technically doing work on the objects, right? So because like it is attracting and there is a force involved, right? Now, whether it is static, whether the object is moving or not, it is secondary, but the earth is always doing work on every object. So in the same way, it's written here that this is the object increases its energy when it is raised to a height because the work is done on it against gravity while it is being raised. And the energy present in such an object is called the gravitational potential energy. So the amount that is stored on the body after it has been raised to this height. So if this was S0 and this is S1, so the energy of the object at height S1 is due to the work that has been done on that object against gravity. Like you obviously need some sort of resistance, right? Like if you are pushing a wall and the wall is not moving, why is it not moving? Because it is exerting an not equal, obviously a much larger force on you, as a result of which you are not being able to push it, but you are also giving some sort of an energy to it, like you're exerting yourself so that you want to move that wall, but the wall is not moving. So in the same way, anything on this earth, due to the presence of gravity, due to the presence of air friction, will always be opposed, right? So that is why you are doing work against the gravity when you are raising the object, and that work done is being stored as potential energy when it is raised through this height. So at S1, the work done will be completely converted into potential energy, and this potential energy is basically with the formula of work that we had studied in the last chapter, in the last session, sorry, it was F into S, right? So now F here will basically be the weight of this object, which is mg, right? So work done, or the potential energy at S1, will be mg into S displacement, which is whatever, let's say this height is h, so h, right? So this is basically the formula of the gravitational potential energy. Okay. Another thing is that it is useful to know that the work done by gravity depends on the difference in the vertical heights of the initial and final positions of the object, and not on the path along which the object is moved. Now what it means by this is that since the vertical height is h, it doesn't matter how you have reached this height. As long as you have reached this height, your calculation will not change. Your calculation will always be the vertical height between the final and the initial position of the body. Since the vertical height is h here, there is no question whether, like, how it reached to this level, but since the total displacement of the body was h, it will always be mg into h. Okay. So now we come to the law of conservation of energy. Now what does it say? It says that energy can only be converted from one form to another. We had discussed about it in our previous session when I had told you that the windmills, when they, like, what is the significance of a windmill? It is basically present there so that it can convert the wind energy into potential energy, sorry, or kinetic energy, right? So the wind energy, as and when being it is moving these blades, basically wind energy is getting converted into kinetic energy. And why do we need kinetic energy? We don't need kinetic energy per se, we basically need the electrical energy from it. So here we can understand how kinetic energy is being converted into electrical energy. Somehow it's a complex process, we don't need to get into that right now. So the wind energy getting converted to the kinetic energy, getting converted to the electrical energy, which is being used as current in a lot of home appliances, machines, etc. So from here we understand that the energy is not exactly getting wasted. It always just changes its form from one form to another, and that is how we get so many forms of energy. And at the same time, none of the energy is wasted, because the total energy before and after the transformation always remains the same. The law of conservation of energy is valid in all situations and for all kind of transformations, whether it is wind energy to kinetic energy or vice versa, whether it is sound energy to electrical energy or vice versa, it is always the same. It before and after, the amount of energy, the amount remains same. So a very simple example for this is that when you are speaking into a microphone, what is happening is the sound energy is getting converted into the electrical energy. Okay, so this is because of the microphone. And when you are hearing the noise, hearing the sound, sorry, it is because the electrical energy of the speaker is changing into sound energy. So this is due to the speaker. But it is never such that you are speaking lightly into the mic and you are getting a huge sound. No, the amount of sound energy that is getting converted to electrical energy through the microphone, that amount only will again get converted into sound energy, which we'll be able to hear. There will be no loss in energy, and that is the law of conservation of energy here. Okay, so its significance is basically that, and this is a very important question, from the law of conservation of energy, we have found out that at any position on Earth, the sum of the mechanical energies, that is kinetic energy plus potential energy, will remain constant. Okay. Or half mv square plus mgh will remain constant. So there's a very easy example through which we understand this. It is by calculating the position of a ball at 3 different positions. Position A, B, and C. This is the ground level, obviously. Yeah. So basically we find out how at all these points we get the same total energy, like the mechanical energy of the ball is conserved at every single point. Okay, so let's start that mechanical energy at A. So here, let the ball freely fall from position A. So now what does this mean? When I say freely fall, it means that it had no velocity, right? So just before falling, since it had no velocity, will it have kinetic energy? Obviously no. So the kinetic energy will be 0, and let us call this height. It's vertical height, mind you, even if it does not look so. So the vertical height, let it be called capital H. So it will be mgh. You know that if kinetic energy at a place is 0, it means that the potential energy is maximum, right? So here at A, there is only potential energy, like the whole energy is stored, like just before falling, right? Because as soon as the ball falls, the stored energy or the potential energy gets converted into kinetic energy. Not fully, but yeah, some of it does. So now mechanical energy at point B. So now let the ball travel a distance of h. Okay, so let the distance between A and B be small h. So now how do we calculate the kinetic energy at B? First we find out the velocity of the ball at B. Now this is from a little bit of the first chapter rather, motion in 1D. So there we had found out that there was a formula v square minus u square equals to 2gh. Since initial velocity is 0 here, we have to find the velocity at B, which is basically 2g, and since it is traveling a distance of small h, it will be h. So v square equals to 2gh. So here we are basically going to replace the v square in the formula of kinetic energy into 2gh. So it will be half m 2gh plus, now this is a little tricky, but if you understand it then you'll never forget it. It's basically potential energy is always the vertical height from the ground or from the zero position or from above the sea level, whatever you have thought to be the zero position. So this height is basically h minus small h, right? So potential energy is always calculated the vertical distance from the 0th position. So here it will basically be mg h minus h. So this is basically mg small h plus mg capital H minus mg small h. So this values get cut off and it is basically mgh. So you have seen that both the mechanical energy at A is mg capital H and it is at point B, it is also mg capital H. So now you're understanding that how it is getting conserved, right? We're just going to talk about the third point here, that is point C. So now since we have considered the ground to be the zero position, so obviously when the ball has fallen to the ground, there is no height left for the ball to cover, right? And since potential energy or gravitational potential energy, it depends, its formula is mgh. Here h is your zero, right? Because there is no height, it is the relative position is zero because you have again gone back to the zero position. So there will be no potential energy at that point. All of the potential energy that was there at point A has been totally converted into kinetic energy. So now our motto here is to just find out the kinetic energy, which will be half mv square again, but this is vc square rather. And what will be vc square? It will be, again, if we use this formula here, again if we use this formula, v square equals to 2gh. Here basically vc square equals to 2gh because the distance it is covered here is the full h. So here we again replace it by half into m into 2gh. So which brings us to, okay, then there's no more space here, I'll just write it like you get the idea, right? It is mgh. So at all the 3 points A, B, C, we see that the total amount of energy, mechanical energy, is the same, which brings us to the conclusion that the energy has been conserved and the total mechanical energy of an object will always remain constant. Our last discussion for today is power. It is nothing but the rate of doing work. And when I say rate of doing work, we know that the meaning of rate is anything per unit time. So it is basically work done per unit time. So power measures the speed of work done, that is how fast or how slow the work is done, rather the rate of doing work or the rate of transfer of energy. This is interesting because if I say that a machine is working very slowly, like for example, a train is working like is like going at a speed of 5 meter per second. Okay, so it means that the supply that the chemical energy that is given to the train, for example a coal train, we know that a coal train works on the energy that is supplied by the coal. So the chemical energy is basically getting converted into the mechanical energy very slowly, as a result of which the train is only moving at 5 meters per second. But if there's a super powerful train in which the chemical energy is getting converted to mechanical energy very fast, the train will obviously run very fast, and it just means that the second train has a higher power engine. Like the power of the engine is much more. So as a result of which the work being done is much more. So in the same way, power is basically a unit which we use to say how much faster work is being done or how much faster the rate of work is happening. So we can write it as F into S by T. Now you know that S by T is basically velocity, so we can also write it as F into V. So now the unit of power is, yeah, so we know that it is joule. We know that the unit of energy is joule. So joule per unit time would have been the correct one, but the SI unit of power is given as watt, which is written as capital W. So SI unit of power, SI unit of power is equals to watt, denoted by capital W. So now when we talk about big machines where the power is a lot, there we basically don't use watt, we basically use kilowatt, which is nothing 10 to the power 3 watt. So we can also use in some cases kilowatt. Now the energy that is calculated on a daily basis, like how much energy is being spent on, let's say, a computer, the microwave in your house, the lights, the bulbs, everything. So to calculate how amount of energy that is being spent in all of these separate electrical appliances, there was a commercial unit of energy discovered or assigned, for which the calculation for the money that we will assign to every electrical appliance and how much money is total being spent by the household on these appliances is calculated. So we came up with a unit known as kilowatt hour. Now I told you that the power is basically nothing but the work done per unit time. So power into time is basically work done, or watt into seconds, which we can also write if the power is like huge amount, we can also write kilowatt, and we can also, instead of writing seconds, we can also multiply it by hour, right? So that is how it came, the commercial unit of energy, kilowatt watt hour. So that will be all for today. We've talked about the commercial unit of energy. We've talked about power. We've talked about the law of conservation of energy and how significant it is, how the total mechanical energy of an object is always conserved at any point above your zero position assigned by you. We've talked about potential energy at a height and how it does not depend upon the route you have taken to raise it to that height. It is about the initial and the final positions. We've also talked about potential energy's definition, how it is the stored energy in an object and why is it the stored energy in the object. And we've done a little bit recap about the kinetic energy, the work, and how the relation between the kinetic energy and the momentum was discovered. So pretty much that was about this chapter. And there was just one small thing. And that is in how in a pendulum always one form of energy is getting converted into another form of energy. That is, the potential energy always is maximum at the maximum height of the pendulum. That is, if this is the 0th position again, and this is the maximum height that it reaches, like A, B, and C. So this is the motion of the pendulum, right? So what we have to remember here is that the kinetic energy here is the maximum, okay, at position A or at the 0th position. And as in when you are taking it to the maximum height, and when the moment it is at the maximum height, its potential energy will be maximum and the Ke will be 0. Again, the same thing. It will come here when again Ke will be maximum potential energy 0 and again vice versa. So if you plot it in a map, so this is how it's exactly going to look like. That at the highest point, basically, if this is like, if this like, both of these points, like point A and point C and point B, let it be like at a height of h. So, and if this is h and this is 0, excuse me. So you're knowing that the potential energy, so like this part of the graph, like this line denotes the rate of increase in potential energy, and this line here is basically the kinetic energy, right? Just draw it. It's getting a little, yeah. So this line is basically the kinetic energy, right? Which is basically 0 at the maximum height, because here all of the kinetic energy is getting converted into potential energy, because potential energy is this total amount of energy that is stored in an object at the highest or the maximum position relative to that of its 0th position. So yeah, this was all for today. Thank you and keep watching us.